In this video, we deal with a second translation theorem concerning the Laplace transform, which says the following. If the Laplace transform of the function f of t equals f of s, then the Laplace transform of the function u of t minus a, this is the unit step function, times the function f of t minus a equals e to the minus a s times f of s. And the similar result holds for the inverse Laplace. So if you take the inverse Laplace of capital F, and this is f of t, then the inverse Laplace transform of e to the minus as times the function f of s equals u of t minus a times f of t minus a. We write the proof and we use the definition for Laplace transform. We have the Laplace, so the Laplace transform of the function f of t is the integral from minus infinity to infinity f of t e to the minus st dt. Now the unit step function is 1 when t is greater or equal to 0, and 0 when t is strictly less than 0. Now let's take a shift of u of t minus a is 1 when t minus a is greater or equal to 0, and 0 when t minus a is strictly less than 0. So from here I can write u of t minus a is 1 for t greater than a, and 0 for t less than a. Now I focus on the Laplace transform of u of t minus a times f of t minus a. So I use the definition here. Is the function here, this product of two functions, times the kernel dt. Now I split the integral from minus infinity to a, plus the integral from a to infinity. From minus infinity to a, the function is this integral vanishes because my function u is equal to 0, so it kills this term here, and I only have the integral from a to infinity of the function f of t e to the minus st dt. I just rewrite it. I go to the next page. Integral from a to infinity f of t minus a e to the minus st dt. Now I need to change the variable u equals t minus a. For t equal to a, u is equal to 0, and from t going to infinity, also u goes to infinity. So from 0 to infinity, f of u, the differential dt equals du, and here I solve for, so it's e to the minus s, and from here t equals u plus a du. So I have the integral from 0 to infinity f of u e to the minus su times e to the minus s times a, and this is du. Now this exponential will go outside because the differential here is du, and I have f of u e to the minus su du. So it's e to the minus sa, Laplace transform of the function f of u is e to the minus s times a f of s. This is a function of s. So the Laplace transform of the function u t minus a times the function f of t minus a equal e to the minus as times f of s. Laplace of u of t minus a f of t minus a equals e to the minus a. Now I use the inverse Laplace transform on both sides of this relationship. It's a linear integral transform. And here the inverse Laplace of this product here. Now at the left hand side I have the function u of t minus a times f of t minus a, and here I have the inverse Laplace transform e to the minus as f of s. So from here the inverse Laplace transform of e to the minus as f of s equals the product of the shifted unit step function times the function f of t minus a. And the proof for the second translation theorem is complete.